Everybody hear me? Yes. Super. Well, thank you very much, Jess, for the very kind introduction, and thanks to Gordon as well for suggesting me to give a talk here. And most of all, thank you to all of you for coming out. I just come here at some speed, actually, from Durham, where I was giving a lecture from 5 to 6, an ordinary teaching event, and I will say, the lecture theatre wasn't as full as this, owing, I believe, to the fact that it's Halloween, something which the students get very excited about these days for reasons that aren't completely clear to me. So on the way here, it suddenly struck me, actually, the place is teeming with people in fancy dress and generally looking slightly horrific. And I thought, I felt slightly guilty that I hadn't made any effort. But I will say, as days go, the number of deadlines I've had today, the number of talks and lectures I've had to prepare, the short interval between the last two engagements, and the fact that the train I'd hoped to get was delayed by 125 minutes. I feel as though today's been quite horrific so far. So I think we're in the right place for the time of year. So I put this up because when I was thinking how to talk about what I'm kind of interested in and preoccupied with at the moment, for me it makes sense to put it in a slightly autobiographical context. So I'm going to talk rather more about myself than I feel comfortable doing, as obviously an entirely reserved and inhibited Britain. So you'll have to forgive me, indulge me, but I'll try not to wallow. And I just said to Gordon that part of the reason I wasn't even earlier getting here is that despite having intended to give a very short lecture, I allowed my inner waffler to take over, and that character is never very far away, so do wave frenziedly if you sense me disappearing. What I've tried to do is go broad and superficial on things this evening, but any one of these things I could talk at for the full 45 minutes, or talk about for the full 45 minutes. So I must desperately try not to. So if you see me sort of kicking myself, it's probably because I'm going on. So yes, I want to talk a little bit about the work I've done, in particular talking about some sort of formative events and experiences which led me to think about the things that I think about, some of the species and systems that I've worked on that inform where I've got to today. So I thought I'd start actually at the very beginning, having been born in Wales, so not quite as, well, actually it probably was as far south as Bristol, to be honest. But I left there aged 8 months, so I can't claim to be Welsh. And moved, in fact, to the Fiji Islands, which I was far too young to appreciate, despite having spent several years there. It didn't do much for me apart from fill me with a sort of a lifelong lust for travel and exotica. which is becoming increasingly problematic as travel is ever more frowned upon. Another formative experience was being absolutely wedded to this series of books. I'm looking around, I'm not seeing much recognition here. Don't know if anybody ever read all the adventure series by Willard Price, but I did about 12 times. These were books about a pair of American lads whose father was a collector for a zoo, so terribly inappropriate these days. And they went around the world having adventures, meeting bad individuals and battling exotic wildlife in every corner of the world. An interesting thing about that, of course, is that the things they were after were always more highly prized if they were rarer. This was a repeated theme, and actually something I will come back to later in this. Something a little more mainstream that I imagine may have informed everybody in this room was an obsession with watching wildlife on one. So I did meet David Attenborough once and told him he had a lot to answer for. But I was so overawed by the experience that the words didn't really come out properly, and he probably thought I was mad. And then, of course, quite relatively late on during my teen years, I read Jules Verne's 20,000 Leagues Under the Sea. I don't know how many people have read that rather than watching the film with Kirk Douglas, which was also fine. But there's an extraordinary passage in this book where so for those of you who don't know, it's about a gentleman, a sort of Victorian gentleman and his manservant who get shipwrecked, picked up by a lunatic in a submersible. And the manservant turns out to be an incredibly erudite and competent zoologist who stands at the windows of the Nautilus, as it's called, and over a span of many pages simply describes and defines every single thing that goes past the window. And I was absolutely captivated with that, and I thought, how amazing to have that much awareness of what's around you, to have that much knowledge of every living thing, to be able to do that. And that really informed my next step, which was to go to Bristol, as Jess said, where I studied zoology. And actually, it was while at Bristol, an early part of my time at Bristol, I was lucky to have as a tutor a man called Bob Savage, who was an academic, really of a different era. Incredible office, very dusty, fusty sort of thing, with lined with shelves, just absolutely crammed with fascinating artefacts, amongst which was a skull very like this. It's just something you don't see anymore. Academics with offices like that, with things that, and I think maybe this is what inspired me actually to go on to become an academic. After Bristol, I obviously needed to repair my finances, so I repaired to the city, but not for long, because I then relocated to Alberta in Canada, which is a very beautiful state, as I'm sure many of you know. And there I worked on a captive breeding program for the swift fox, which is a species of prairie fox which had been extirpated from Canada in, I think, the 1920s, probably largely an accidental byproduct of poisoning campaigns for coyotes. And I was working at a captive breeding facility in the foothills of the Rockies, so this heavily treed, very sort of montane type habitat, but actually releasing the foxes down in an area called Grasslands National Park, which is the one pictured down here. And that's in Saskatchewan, sort of southwest corner of that state. Proper open rolling grasslands. And we took the foxes down there and we gave them what's known as a soft release. So we put out accommodation for them. We even provisioned them in their early time out there. But the big problem for the foxes was the coyote, very abundant, ever more so since the eradication of wolves in the area. And coyotes, as suggested by the Wile E. Coyote, the cartoon figure of fame, are incredibly resourceful. They're extreme generalists, and as we know, it's very difficult for an obligate predator with a sort of single prey to drive that prey to eradication, because of course when the prey becomes scarce, the predator can't find them anymore, they decrease in number and the prey become abundant again. But if they're a tremendous generalist, like the coyote, able to take many, many different types of prey, from carrion to tiny rodents all the way through to full-grown deer, then it's very difficult for a small to mid-size prey item to get a foothold. And I was very conscious of that, very conscious of the difficulty for these swift foxes of trying to establish from a situation of great rarity relative to their predators. And it wasn't actually helped by the fact that at the captive breeding facility they had a domestic dog that moved fairly freely around the enclosures and possibly gave the foxes a false sense of security about their own vulnerability or lack thereof. So plenty to learn from this experience, not all of it good, but all of it educational. So obviously following a couple of years out in Canada, back to the city with me to repair my finances, but I didn't stay there long. I moved, again, as Jess said, I moved down to Canterbury in Kent, and had the good fortune to conduct a master's project based out in the Bali Mountains National Park in Ethiopia, which is an incredible landscape, one that I think very few people think about when they think about sub-Saharan Africa. It's packed with interesting species that you don't see elsewhere. It's a real centre for endemism, so unusual, unique species, such as that Menelix bushbuck, which is an absolutely beautiful animal. Mountain nyala, one of the commonest species, but another of Ethiopia's endemics, which I was there principally motivated to work on, was the Ethiopian wolf, also known as the simian jackal, it used to be known as, but owing to genetic studies which placed it closer to the wolf than the jackal, and also the generally bad association that people have with jackals relative to wolves, there had been an attempt to rebrand it. And I was there, we were the first group of people to visit the area and try and do a sort of systematic count of mammals out there. Since, I think, 1985, so by this stage this was 1996, there'd been a civil war in Ethiopia in the early 90s, which had resulted in a lot of disruption and a general loss of control. I mean, it was no bad thing, don't get me wrong. The previous dictator had been displaced, and a new, ostensibly democratic government had been set up in his place. But it had led to a general relaxation of the extent of control in the national parks and an expansion of human activity. So these what are known as tukals, the little round houses, were proliferating all over the open plains of the area. The people brought domestic stock with them. The domestic stock were potentially outcompeting wild herbivores for grazing. They brought domestic dogs with them, which were swamping the Ethiopian wolves in number and leading both to diseases, things like canine distemper and rabies, but also to what's known as genetic introgression. They were breeding with the Ethiopian wolves and producing these sorts of individuals, very often sterile hybrids. So there are a lot of interesting lessons there, once again about rarity, about vulnerability to external factors, and about, again, this problem of swamping by external forces. The other thing I learned through many extremely hard hours on horseback, on a saddle which basically amounted to a wooden A-frame, and with buttocks somewhat depleted by 6 months of amoebic dysentery, I discovered that fieldwork is arduous, and monitoring the abundance of mammals is also very arduous. So, needless to say, on return from that, there was a bit more time in the city to repair my finances, but then I moved to the University of East Anglia, where I think my obsession with zoology, seeded by Jules Verne, began to give way to a more rounded interest in ecology. And there I worked with a guy called Bill Sutherland, who had just written a book about, well, it's called From Individual Behaviour to Population Ecology. And it was essentially about what we can learn from overall population dynamics about the ways that individuals behave. And one of the things that was particularly fundamental to that was the question of how behaviours change with population density and what are the impacts of those changing behaviours on population dynamics. And I think one of the most overt and sort of widely acknowledged forms of that behaviour is the type of behaviour that results from crowding. So where individuals in a population become superabundant, we see really obvious manifestations of competition. We see things like competition for breeding sites, competition for food, competition for water and other resources, and potentially even competition for mates. And all these forms of competition underlie a very characteristic form of population growth, this idea that populations starting from a low ebb, which was the bit that interested me, both in the context of the swift fox and that of the Ethiopian wolf. Populations starting from a low ebb typically show very high population growth because they're not competing with many others. So they can grow very rapidly, and then that growth, sort of multiplied by the number of individuals, gets higher and higher as individuals become more abundant. But then competition really starts to take over, and we see population growth actually beginning to decline until the population stabilises at what's often referred to as the carrying capacity. And this is an absolutely, these days, I mean, it was bitterly 100 years ago, wasn't necessarily particularly recognised. 70 years ago, it was bitterly contested among ecologists, but now I think it's broadly accepted as probably one of the major phenomena of population growth. And it's associated, we look at it in a different way. If we think about how rapidly the population grows per capita, then the presumption is that that is highest when there are fewest individuals in the population, and that in general it declines as the population gets larger until we get to a point where the population is so large that there's only just enough resource to go around between everybody for them just to replace themselves. And then we reach a situation with no growth and the carrying capacity that you see up here. And the result of that underlies lots of ecological phenomena, perhaps the most famous of which is this idea that you get, because we got tiny numbers here, a very low abundance of individuals multiplied by a very high population growth rate. Doesn't matter how high that population growth rate is, we get very few individuals added to the population because we've got so few to start with. At the other end of the spectrum, we've got an enormous population, but only just enough to go around. We have no growth, so individuals are just replacing themselves year on year, so there's no real addition to the population. But the idea of this, what's called logistic growth, is that about halfway in between, the population's growth is maximised. So population growth rate per capita is intermediate, but there are large numbers of individuals out there. And so there are the most possible individuals produced. And this is the point I I guess it was probably in the 60s or 70s that this link was made, and people said, well, actually, if you can harvest a population, if you can remove enough individuals so that you maintain it at half its carrying capacity, this is the point known as the maximum sustainable yield. So you can take the most individuals off every year and the population will still replace itself. So that's a fundamental ecological principle, but one of the most overt illustrations, I suppose, of how changing behaviours as populations grow lead to changing attributes of a population. And there are lots of examples. You know, the idea of this sort of linear pattern of declining growth is simply a conceptual notion. Some species might show it, like this North American bird. Other species might show something very different, where maybe population growth is fairly stable over a broad range of population sizes and then sort of crashes quite rapidly once the population exceeds some level. And although it's still debated, other species seem to show a slightly different pattern where density dependence kicks in most strongly at low sizes and then gets more gentle as we go on. The point is that all of these are examples of where population growth rate per head is highest at low population sizes and lowest at high population sizes. And it was this that Bill Sutherland wanted me to look at. And in particular, and relevant to some of the work that Jess does, he wanted to know, does this really apply to obligate social species? And so I looked at this with a couple of different case studies. And the first of them took me to the mountains of southern Switzerland, not too far from St. Moritz. And I worked in this valley where a group in Austria had just an incredible study looking at alpine marmots. So he's a member of the squirrel family that you cannot help but notice if you're in the Alps. And they live in family groups. And the interesting thing about marmots is that they hibernate together within their groups. It's what's called social thermoregulation. It's an extremely hostile environment in the winter. It's very cold, very, very deep snow cover for a long period, absolutely no access to grazing. And so these animals simply hibernate, and they hibernate together, and their sort of shared warmth keeps them going. And one result of that is that if there are too few individuals in the group, then there aren't enough individuals to keep them warm, and so survival over winter is profoundly inhibited. And this incredible study, set up by a guy called Walter Arnold in Austria, had every individual in the entire valley instrumented with an implanted transmitter that measured its body temperature and its heart rate. And so Walter could sit in his office in Vienna and know what every individual in this valley in Switzerland, in a remote part of Switzerland, was doing, know when it was kind of aroused from hibernation, when it went back into hibernation, when it first came out and started to move around in the spring, and of course, how many of them died and in what context. He could also pinpoint where they were from this system of antennae all the way up and down the valley. So a really incredible study to work on. And what we were able to do is construct population models that had varying degrees of realism about these within-group dynamics. But what we showed, and this is essentially the same kind of plot that I was showing earlier, with per capita growth rate on the y-axis and population size on the x-axis. What we're able to show is that models that accounted realistically for this phenomenon of within-group dependence on each other showed that, yes, there was a sort of carrying capacity up here and population growth rates got higher above that level. But actually, as the population declined again, and this is going way beyond what we observed in the wild, but the sort of emergent property of putting these behaviours into the model showed that as the population declined, the growth rate of the population would also decline until actually at a certain critical point, the growth rate of that population would become negative and the population was pretty much doomed to extinction. So what you can see is that, yeah, the range of densities that are seen in the field, population's pretty robust, just looks like a normal picture of declining population growth rate with increasing population size. But in a realistic population model, we can see that population growth would also decline at small population size. And one consequence of that is that the alpine marmot is quite a heavily hunted species, and we were able to show that as a consequence of this behaviour, it was extremely vulnerable to overexploitation. Whether you set your quotas as a sort of number of individuals that could be removed every year or an amount of hunting effort that could go in every year, there are these very sort of abrupt shelves in which the number of individuals taken off could actually lead, rather than to a robust population that allowed you to take individuals every year, to a population collapse. And this is a phenomenon known as positive density dependence. So what I talked about before, where we've got declining population growth in response to population size, is what's called negative density dependence. But what we were showing here was that group behaviour, the obligate sociality of the marmots, led to something called positive density dependence. And this is something that was recognised by a zoologist back in the 1950s. A guy by the name of Alley, Warder Alley. And I think at the time it was viewed as a bit whimsical, and his examples were often slightly whimsical, and most people had ignored it. And negative density dependence was very much the prevailing view of how population dynamics change with population size. But we thought about it a bit more, and there are all sorts of reasons why you would expect individuals to be better off in populations that are larger than very small sizes. And obviously, perhaps the most basic of those is that if you're a sexually reproducing species, you need another individual with whom to reproduce. So in very small populations, just by chance, you can be all male or all female. The more of you there are, the more likely it is that you'll find compatible mates of the other sex. So larger population sizes can lead to greater breeding output. Bill Hamilton, who was a famous zoologist, had showed long ago that individuals were more likely to group together when the risk of predation was high. This was a figure taken from his paper, The Selfish Herd, which showed that even individuals just trying to get away from the periphery of a population where predators might most easily access them, even just that kind of behaviour could lead to aggregation and sociality as individuals tried to reduce predation. And then there are all sorts of other mechanisms associated with sociality that suggest that individuals might be better off in company. The picture here of guillemots colonially nesting is actually associated with what I was talking about with the swift foxes, which is this idea of predator satiation. So a lot of seabirds try to reproduce all at the same time, all in the same place, because their predators are largely constrained in number throughout the rest of the year. And then if there's just this massive pulse of new offspring, then hopefully the predators can't be so abundant that they'll overwhelm all the new offspring available. There are mechanisms like collective vigilance that we see famously in groups like the meerkats, collective hunting potentially in large carnivores, and equally collective defence of prey. So things like these wild dogs trying to defend prey from hyenas, and it's been shown that wild dogs need to be their groups need to be reasonably large in order for this to be successful, because you need about 4 wild dogs for every hyena that comes to try to take your prey. And in addition, you need other members of the pack to stay behind and look after offspring, and generally to be vigilant as well. So lots of different mechanisms that can lead to positive density dependence. And this is one depiction from a paper, published by another group, but in a sort of pair of papers that we put out together. And this was just showing the difference between the sort of general supposition of density dependence, or what I would term negative density dependence, bringing population growth down as the population gets larger. So we have this relationship where actually population growth gets down as the population gets smaller as well. And that leads to an interesting problem, because carrying capacities are typically thought to be stable, because below them populations have positive growth rates, so that pushes them towards the carrying capacity, and above them populations have negative growth rates, so that also pushes them towards the carrying capacity. By contrast, you have another equilibrium down here where population growth rates become negative, but those are unstable population equilibria. So above that, the population is growing positively, so that pushes it towards this end of the graph, towards carrying capacity, but below it, the population is declining, and that pushes it back towards a population size of 0. So the idea was that this positive density dependence can actually introduce real problems for rare species, or species that are at low abundance, and lead to at least one manifestation of what's sometimes referred to as the extinction vortex. So the problem where small populations just continue to get smaller and smaller by virtue exactly of their small size. I said I'd refer back to Willard Price later in this talk. I mentioned his thing about rarity and how the rarest animals were always the most prized. And Frank Corchon, who produced actually that figure on the previous slide, who was a friend back in the day when we were working on this, Frank actually had a paper looking at this and looking at the impact of economics on population dynamics. And what he pointed out was that if a resource, something you extract from the wild, has a constant value, so you're able to sell it for a constant amount, as it becomes rarer, it gets harder and harder to find, and therefore more and more expensive to acquire. And that's what this blue line shows. And that leads to a sort of stable, what's known as a bioeconomic equilibrium, the point at which the cost of acquisition of this thing outstrips the value you can get to it. So you basically stop exploiting it at that point. And that's great. That means that things are fairly robust to overexploitation, because they become uneconomically profitable to exploit once they become rare. What Frank pointed out, though, was that if the amount you can sell something for increases as it becomes rare, that can actually change these dynamics and lead to what he termed an anthropogenic alley effect, so positive density dependence, where all of a sudden at low population size, the value of the thing you're exploiting outstrips the cost of finding it again. And this is very often where the Hunt brothers were operating. And he went on to show that this does apply. We do see this in a lot of cases. So we see it. This is for a mammal. These are goats of various types, things like mountain goats and so on, and showed that the rarer they become, the more valuable they become. So these are probably cost of hunting tags. Likewise, these are within taxa, so for different groups, these are species that are CITES listed, so there's a ban on their international trade, and these are species here with the filled-in symbols that are free to trade. There's no prohibition against that, and he showed in every case the value of those that are rare, and therefore international trade is banned, far outstrips the value of those that are reasonably abundant. So another mechanism there, which sort of harks back to my early reading. So I went on to look at this in another social species. So I moved then to, this is the sort of outskirts of the Kalahari Desert in northern South Africa. And I was looking at the meerkat on another absolutely fantastic study, which many of you will have heard of, but some of you may even have seen something of this study. I know there was a TV program, I'm sorry to say I never saw it, but one called Meerkat Manor for a while, looking at these, basically turning the lives of these animals into a sort of soap opera. This incredible study had a huge number of highly habituated groups that you could get very close to. You could observe them going about their daily behaviour, and you could even coax them onto scales morning and night, just the sniff of a hard-boiled egg, and they'd very obediently hop into a scale pan for you. So again, a study where you could learn an enormous amount about the fates of individuals and how those were affected by the shifting dynamics of groups and populations around them. And again, we could see that there were lots of things that improved as group sizes increased for these within this species, within meerkats. So we saw, for example, that the survival rate of offspring up to about 6 months old increased as group sizes increased, more individuals to look after them, to feed them, to babysit them. And we also saw that the probability of a female producing a litter that actually survived until they emerged from the burrow also increased. This is a dominant female here. These are actually subordinate females who are very unlikely to produce litters, and the more so in larger groups, where the dominant female exhibits almost total despotic control over the lives of others. And we were able to use that information again to model aspects of their life history, and particularly to model this trade-off between whether individuals should disperse and try and go and breed or remain within their current group and help. And again, we saw that when the population is low and groups are at fairly low size, it makes much more sense for individuals to stay with their current group, forego reproduction themselves, but help probably the related dominant individual to reproduce, rather than going off trying to breed themselves, but going typically in very small dispersing cohorts that are very vulnerable to predation and other problems. So again, an example of these alley effects, these problems of low population sizes, which make the sort of traditional view of population dynamics rather different. I'm keeping half an eye on the time here, and I'm going to gloss over this, but just to say I did break with my mammal obsession for a while to work on farmland birds, but more on that if there's time. And then after that, my feet became itchy again, and I moved to Wyoming. And bizarrely to Wyoming in America, not to study anything in America, but actually to study this animal, the Mammal tiger. My boss in America was very close collaborator with the people who worked on the Amur tiger, and we were funded by the US Forest Service, which is something slightly bizarre, but I could explain it if needed. Working in the Russian Far East, so in these coastal, what are effectively rainforests in the Russian Far East, areas that are subject to high amounts of logging, and also a lot of illegal hunting and offtake of prey. So there's a lot of competitions, right? That's a wild boar down in the corner there. A lot of competition between human hunters and the tigers themselves. And I think that's a form of threat to tigers, which is very often overlooked. I think everybody thinks, oh, tigers, poaching, overtly problematic, habitat loss, of course, catastrophic. But something that people don't think about so much is how much prey tigers need in order to survive, and how even just taking relatively small amounts of prey out of the habitat can cause them to struggle. My focus there was on looking at long-term data and trying to make sense of long-term data of prey abundance, which I did, looking at the abundance of different species of deer in different habitats. And overall, I showed that these were tigers living at some of the lowest prey densities of any recorded tiger. So this is a plot of tiger density against prey density, and you can see that the prey biomass density extends way out to the right here, but our Amur tigers firmly almost as low as you can go as far as having any viable habitat for tigers goes. And that prompted a whole range of questions still along this theme of rarity. And how rare can things get? What constitutes a viable habitat? And provoked, and you can think of species just living in really improbable situations, often desert situations like these three examples here, but also what is effectively a desert, things like polar bears living at phenomenally low densities in habitats that are just expanses of empty wilderness, often devoid of prey, sadly becoming ever more so. But in discussions with the people who ran the Siberian Tiger Project, it really provoked an interest in thinking about how rare can things become, how rare can their prey become before they simply can't persevere. And I think there were kind of three ways we could think about this. We could think about alley effects, these positive density dependence. Where is that lower threshold when population growth rate becomes negative and populations decline to extinction? There's a whole branch of conservation biology which deals with something called population viability analysis, and one of the ways that people use these essentially population models is to identify the lowest possible number in a population that could be viable into the future. So we can maybe look at those. And also we could take what are sometimes referred to as macroecological, so kind of global approaches to asking how rare things can become. The problem with thinking about this in the context of alley effects is just what I mentioned earlier, the fact that this is unstable down here. If a population gets down to these low sizes, it pretty much declines very rapidly to extinction. You don't get the kind of repeated estimates of population growth that you need to characterise where this threshold lies and how population growth rate changes above and below it. You get lots of data at this end because populations are forever fluctuating around here, and so you can get repeated measures of how rapidly they grow. But down at the other end, it's almost impossible to show this, and I think that's partly why alley effects have been sort of overlooked for a long time in the ecological literature. This whole branch of minimum viable population, or investigations into minimum viable population, has been studied very intensively by a group in Australia, actually. And they became obsessed with the idea that everything pointed to the idea that you needed 5,000 individuals, almost regardless of what kind of species you were dealing with. You needed 5,000 individuals to confer a high probability of safety into the future. And this was even branded a magic number. And they said it didn't matter what kind of taxon you were dealing with. They looked across lots of different taxa. They said, well, there are no statistical differences in all the estimates that people have made of how many you need to be secure. So this must be a magic number and it must work. And they actually proposed that we have an index based on it. And the further you were below 5,000 individuals, the more negative that index became. And they said that you could use this in a way if you wanted to prioritise conservation and focus on those things that were most worth saving. You could maybe say, well, which one has the highest, what they called the safe index? Let's focus on that and forget about the ones that have lower indices because they're not worth trying to save down here. So things like this Javan rhinoceros would go by the board. And I got a little bit worked up about that at one stage, and with colleagues pointed out that 5,000 wasn't a magic number, that the only reason you couldn't see variance between these different taxa is that there's so much variation within taxa. Estimates of minimum viable population sizes for any one species vary enormously over multiple orders of magnitude. An example is this for the grizzly bear, where there are estimates that 400 grizzly bears is a secure population. Equally, there are estimates that say that 44,000 grizzly bears is a safe population. And the reason for these enormous discrepancies is that people who come up with this don't account for the threats. These different populations are under radically different threats. And, of course, if you can get rid of the threats, then a very small number might be secure. There's also genetic evidence, but I'm not going to talk much about that. But above it all, what good does this really do us? How does it help us to conserve things? What we should be interested in are what are the threats to these things, not how many do we need. So that put me on instead to looking at these macroecological approaches, and this is the last thing I want to talk about. And in a way, what I showed earlier, this plot for the tiger was a sort of macroecological approach. What I'm talking about is data drawn from lots of different areas, potentially across lots of different species. Here we've got data from lots of different tiger populations across lots of different areas, which shows us a pattern that we might not see if we just focus on one population. But we can do more than that. We, together with colleagues, we gathered together all the data there was on prey abundances that different sized carnivores depend on. And we asked, well, can we explain how low that can get? And we constructed a simple model that was based on how they move around their habitat, how much energy they need, and we estimated this that this red line would be the basically the lowest viable quantity of prey that a species of any particular size could cope with. I was initially alarmed to find this data point for an Arctic fox population way down here, way below what we thought a species should be able to cope with. But actually greatly relieved when I pointed this out to a collaborator and he discovered he'd made a typo and putting the data in, and actually it should lie very neatly just above the line there. And then another macroecological approach we took was one based on looking at population densities, just population densities of lots and lots of different species, wherever they've been measured, and looking at those in relation to their body size. And what you often see is a very strong negative relationship between these two things. Small things are very abundant, big things are pretty rare. And actually this is interesting, and people have been very, very interested in this for a long time. because the slope of this relationship is minus 3/4. It's what's known as a 3/4 power law. But what's interesting about that is that we know that we've known actually for about 70 years that the energy requirements of species scale in exactly the opposite way with a positive 3/4 power law. And the consequence of that, if you put those two things together, is that the energy that a population of organisms removes from the environment per unit area should be exactly the same whether we're dealing with a mouse down here or an elephant up here. And one of my colleagues used to like asking me, what would make more of an impact on the Serengeti, if you killed off the small rodents or if you removed the elephants? And on the face of it, at least, all else being equal, and I admit that all else is not equal, but it should have pretty much the same consequence. It should have the same impact on how much extra energy is in the system. That's what's known as the energetic equivalence rule. But one thing that people had thought about very little in the context of these plots is just how much variation there is around this line. You get things that are orders of magnitude more abundant, so 10, 100 times more abundant, and you get things that are orders of magnitude less abundant for any given size, so maybe occur at 100th of the population density. And my real interest is, well, what defines this lower boundary down here? How rare can things become? And to answer that, this is quite recent work. I've been looking at how foragers move around in a patchy environment, how well they know that environment. Do they just search systematically, or do they move quite purposefully from one patch to another? And depending on how they do that, we get different predictions. If they move around systematically with no real knowledge of the habitat, we get these predictions here that this should be the lowest possible viable population size for both mammals and birds. And if they're quite targeted and show good knowledge of their habitat, we get this rather lower prediction that they can actually tolerate lower population densities. And if we look at that in relation to the actual densities that we observe, we find that reality is somewhere in between that. Just occasionally, and bear in mind that it's very difficult to measure these densities, just occasionally we get densities which appear to be right down there at the point where individuals are moving around with a really good understanding of their habitat and where the food is. But mostly, for any given size, individuals can become rarer than what we would expect if they were moving around with absolutely no idea, just systematically searching their habitat. The other thing we noticed when we were looking at this is if we tease these out into herbivores, which are green, omnivores, which are purple, and carnivores, which are red, and then we look at human population densities, we can look at densities of humans. All these open circles down here are sort of either estimated historic densities or estimates of current hunter-gatherer groups, so groups who are living much as we would expect they would have lived for millennia in relation to their habitat. And we see that these hunter-gatherer groups lie very neatly within the sort of 95% confidence interval of all other animals. Not only that, but actually if we separate them out into groups that have a largely carnivorous diet, fairly omnivorous diet, or a herbivorous diet, we see that they show the same sort of ranges of densities as those seen in this plot for all other wild animals. So what that suggests is that humans, before we kind of modernised, were constrained in exactly the same way as other animals in the densities they could reach. What you notice here, this actually shows the distribution of modern societies, I think, by country. The average global density of humans now exceeding the sort of 95% confidence limit around here, and the urban maximum just orders of magnitude higher than we would expect a wild animal of comparable size ever to be able to reach. And I think that just underlines rather the extreme impact we'll have on the environment around us. So just to summarise, I think I've been lucky enough to travel and work on a wide range of systems, but all of my experiences have kind of highlighted and piqued my interest in rarity, the problems of rarity, and the question of how rare things can become. And we can think about that in lots of different ways, but I'm particularly interested, my title was micro to macro and local to global, so I'm particularly interested in how these decisions that individuals make and the way they interact with their habitat, the way they move around that habitat, exploring for food, can aid our understanding of how these global patterns emerge in terms of constraints. But, and I emphasised it previously, I'll emphasise it again, low density populations are hard to study, they're very seldom studied. Our understanding is very much skewed towards populations that are abundant, because why would you go out and try and study something that you can barely find? So I think more kind of community-wide monitoring is a good thing, which, and Jess very kindly mentioned MammalWeb at the outset of this, and I'm very pleased to see Roland there, who's one of our earliest contributors to MammalWeb, one of the most prolific contributors, and who captured, I believe, this photograph, which, given the lighting, you can probably only just about make out, shows the tail of a ring-tailed coati living not far. Oh, wow. Well, you could have done if it was still there. But anyway, for those of you who use camera traps, very much encourage you to contribute to MammalWeb, and even if you don't, have a look at the site and help us out with some classifications. So happily, that's exactly where I was going to stop. Thank you very much for listening.